everyone. Welcome to Under the Microscope. I'm your host, Pranoti, and today we have with us Sofia Ferreira Teixeira, and she's going to tell me all about how she's going to make my phones faster and my laptops faster, and by that extension, all the devices faster. And I'm going to ask her all kinds of questions related to material science. So Sofia is a postdoc. She's a postdoctoral researcher at the CIC nanoGUNE Institute. And I'm going to ask her, what does that stand for as well? It's in Spain. It's in the northwest of Spain-ish, sort of.
East.
Yeah, east. Great. My geography is amazing. So, well, welcome, Sofia. How are you?
All fine. Thank you for having me here. And yes, I'm originally from Portugal, but I'm now in the northeast of Spain in a region called the Basque Country. And that's why the name is actually nanoGUNE, because Gune is place, let's say, in Basque. So I'm working at the nano place.
I said it's in the west, but it's actually in the east. And east is also where Barcelona... How far is it from Barcelona? Just give me that.
Oof, that's a good question. I actually don't know. But if I can give you a better reference, I'm 20 kilometers away from France.
Okay, so, that's all good. Okay, yeah, that works better. I need to know where to go when I'm visiting you, right? Because I'm gonna make it. It is actually already been my mission to visit all of my curators of the past 5
You're going to love the city.
Seasons. So yeah, I'm looking forward to that. Let's get started with understanding your research about how you're gonna make my and everyone else's phone fast. How are you gonna do that? Please tell me about your research in super simple words. Tell me.
Simple words. So pretty much how we can make that happen is to find materials with better properties or new properties, it depends, that can make our life easier, because then we can make new devices that can make actually our phones work faster. So one of the ways we can make this work is with Spintronics, which is a big word, but it's a big word made of two words. That is electronics of spin. And electronics, well, that's a bit easier, let's say. It's the thing you have when you plug something, that's electricity. But with the spins, and the spins are a property of the electrons that, much like they have a charge, so the electrons moving, let's say, it's what makes the electric current. They also have a spin, and that can also create spin currents and create several other things that we can use to then create devices. We create a lot of things to then make our phones go faster. I don't know if this is in a simple term, but that's like the very simplified version.
It is definitely in simple terms. So just to oversimplify this, I'm going to try to oversimplify the oversimplification. Good. So the electron is going from point A to point B. While the electricity is going like this, like in a linear fashion, so to say, it's also like the electrons are dancing while they are going from point A to point B.
Yes.
How they're dancing, that is what the spintronics is. This is something you know, but it's basically electrons are twirling, whirling, moving around, doing stuff, spinning, basically, while going from point A to point B. And this is what is going to make our devices, electronic devices, faster.
Yes, so how we control that spinning, so the magic of it is that we can control that spinning with the electricity, so the charge current. And how we control it and how fast it can go and how long it can go. So certain materials allow us to do this better or not, or allow us to do this in a way different than the others. And that's what I do, try to see how we can control them, how we can control this spinning of the electrons. That's what I kind of do.
Okay, I have so many questions, but what is the shortcoming of the current materials or setups that we use? So what is the value addition of these new materials or the new techniques that what is the difference here?
So the first obvious answer, and literally kind of first sentence I had on my PhD defense, is that 4% of the energy consumption of the entire world is already these devices. So that's a lot. and it's just bound to increase and increase and increase and increase. At the time where more and more people need to have electronic devices because we are more and more dependent on having access to the internet and so on. So we need to find new ways to do the same things, or to do the same things in a different way as well. It's the same, but to make them faster. Well, to make them faster, to make them more energy efficient, and also try to make them faster. So Spintronics would do these devices in a different way. It will be based on different effects, on different materials, but we could make certain calculations, or for example, certain memories that will be more energy efficient. And that can maybe if you look at just one device using these techniques, it wouldn't be that much energy saving thing. But when you add up the amount of microprocessors, the amount of bits we have in our phones versus the number of phones in the world, it will be a big change. So that is the first obvious answer. And then the other one that I was kind of spoiling in my explanation is that for certain processes, the devices based on Spintronics could be faster. And that's also a good thing, because one of the problems that we're currently reaching is that the speed of processes in our phones, it is scaled exponentially, but it's getting to a limit. And that also comes with the limit of the size, because if we look at a normal transistor, and this was actually first predicted back in the 60s or 50s, I don't remember, by Moore, which was, I think, correct. Well, don't correct me, but correct me in the comments. The first president of Intel, he predicted that the number of devices, number of microprocessors, for example, that will fit, or number of transistors that will fit, will double every other year. So it will be an exponential growth. But the problem is we're reaching the end. We cannot go smaller. We cannot go smaller than an atom. So we are getting to a roadblock. We cannot go faster. We cannot go smaller. And we also need to go more energy saving devices, like I said. And there are several solutions around there, several researchers working in several approaches. And one of them is Spintronics. So that's
how it is kind of connected and makes sense. That makes sense. Okay, that makes a lot of sense. So, or what I'm curious about is how did this, because this is a completely new field for me, right? And I'm sure for most of the listeners as well. So how did you end up being a postdoc 20 kilometers from the French border in Spain and doing this research in spintronics with electronic and magnetic properties of the material? So please tell us about your career journey so far. How did this happen?
It's a very good question, and a very, very interesting one, because at the same time I had it easier, but it's an interesting, it shows how science works. So I decided to do a bachelor in physics because actually when I was in high school, I participated in a 1 week long summer school of physics for high school students. And I felt at home in the physics department. So I felt, okay, this is where I need to be. I was that typical nerd in high school with good grades, and everyone was telling me, go to medicine, go study that or something. But I didn't know exactly what I wanted. It was either maths or engineering, something like that. But then I was in the physics department, and it was like, it's this. And in the bachelor in physics in my university in Porto, in northern Portugal, there is something called extracurricular internship programs. So you can spend the second semester of the year, so from February until July, sort of, working with a postdoc, with a PhD student, with a professor, with whomever wants to have students join their labs, or if it's theoretical, their computers, let's say, like code. And so I sign up for internship that I don't remember the exact wording, but it was like energy conversion based on cars, on the automobile industry. And I remember my friends that were more into theoretical physics saying, you signed up for that? That sounds so engineering, like, whoa. And I was like, well, but the effect sounded interesting. Thermoelectric effect, that sounds cool. And I had an interview with the professor. Spoiler alert, it ended up being my PhD supervisor. I got it. I got that internship. And what we were doing was to work with the thermoelectric effect. which is something, okay, detour, we're working on spintronics, but now thermoelectric effect. Something, so it's a property that certain materials have that converts, well, all materials, but some do it better than others, convert electricity into heat and vice versa. So now you may understand where cars come from, because if you had a long drive and you put your hand in the car, it's going to be hot. So it's trying to take advantage of this waste heat around us. That is, I think the number I used to say in talks back in my bachelor's and master's was 60%. So there's a lot of energy around being wasted. And so my internship was trying to optimize the geometry of these devices. And that evolved into trying to optimize the materials. And that was until I had to decide what to do for a master thesis, still with the same professor, working the 3 years. And it was like, oh, for a master thesis, we can try something different, because if it doesn't work, the goal of a master thesis is for you to know how research works, to go to a lab, to gain experience, to learn, because you're a master student. So I don't know so it was 2016, 2017. So the Nobel Prize in Physics in 2016, it was for topology. You know what? The materials you've been working with are topological insulators. Do you want to try and study these materials for this thing? And I was like, yes, let's do it. So that's how I started working with topological insulators, measuring their electronic transport properties, because that was the big background of my group. And then some reports starting to appear of combining them with magnetic materials. And another big background of my group was magnetic materials and like spin valves, and again, Spintronics. And so I started combining both of that background. And when it got to deciding what to do for a PhD, I was like, okay, I like working with this, my supervisor. And for a PhD, for me, and what everyone said, and I agree 100%, one of the most important things, if not the most important, is the relationship with your supervisor. Having someone behind you that when you're at your lowest and everything is going to hell in the lab, it's still, no, go, continue. It's like that understands you. And I had that because I was working with him for 4 years already. We continued on the topic. And we continue to explore these materials that we're fabricating as a thin film, so nanometer scale, with the magnetic materials, with all the expertise of the group and expertise of my other co-supervisors that were also, I spent some time in London, so also went there to do some measurements. And that's how I ended up working in Spintronics. So I went from thermoelectrics to, oh, these materials also do something interesting. Let's look at that. Oh, if we combine them with something we know, oh, let's look at that. And this is where I am. At the end of my PhD, I wanted to do a postdoc. I didn't want to continue in Portugal. I would go anywhere. I was interested in going anywhere. I applied anywhere that had a position opening. And I ended up here, working on the other side of the coin first, working on the magnetic part, not so much the topological insulator or that type of material part. And yes, that's how, because the group here has a lot of experience. Fun fact, one of the jury members of my thesis on my PhD was one of the group leaders of my group. So there was already a connection there, sort of. So they had experience in the field I was starting, let's say, with my PhD. And I applied, and here I am. And that's it.
That is so cool. That is so cool. So thermoelectric, topological insulators, 2D materials somewhere in between, like all kinds of, and now with spintronics, with like electrical properties, magnetic properties, and the spins of the electrons. That sounds really, really, really cool, I have to say. It sounds very cool. And I'm pretty sure you are also involved in a lot of interesting research projects, of course. Of course, it's like from your internship to like even from your bachelor times and everything. Yes. If you have to pick one research project, just one, that you're most proud of, or the most fun or quirky one, could you pick one research project and explain it to us in super simple words in the section we called In Other Words? Go.
So it's hard to decide on one. Extremely hard.
I know, it's a tough question. I know. But I love putting my guests on the spot. So,
but the first answer that comes to my mind, because not so much, also the scientific part, but not so much scientific part, but how it kind of shaped my path is all the way back to that first internship and others I did on thermoelectric devices. So why do I think that is a project I really like? First, it was obvious what was the application. So I was studying physics. I didn't want, I don't have a profile for an engineer, but I still wanted to know that my work could have an application. And with thermoelectric devices for cars, well, that's obvious to start with. And then I was, a bachelor student. We think we know zero, we know nothing. We know the PhD students are the smart ones. And then you get to be a PhD student, and that's not the case, but different story.
That's a different conversation.
Different conversation. So I was doing some simulations, all happily learning how to simulate stuff in the software I was using, understanding what is the thermoelectric effect, all those equations and all that. And it gets to a point where I start having results, and it gets to a point where my supervisor goes, maybe we can publish this. And I was like, how? Publish this? This is just work from an undergrad. There's no interest. Nobody will be interested in this. I was like, no. Write the paper. Start writing the paper. I'm like, how do I write a paper? I never wrote the paper before. Do it. I'm here to help you. And that was one of the great things of my old supervisor, because he lets you learn and draft, because that's the point. You are not going to have the first thing you do perfectly. But with that iteration, that's how it goes. So I learned that. And that paper suffered a bit. Getting the first submission we had, it got rejected. So I learned how to deal with that. And then the second one went through, but several rounds of discussion with the reviewers. So I learned how to deal with that, and it got published. And I was like, wow, amazing. I'm happy. But then it still gets citations to this day. And I don't know, so I still kind of think as an undergrad, I don't know how the work is so obvious. An undergrad could do it, but no one ever bothered. And it was something that is important. And this work, so obviously the thermoelectric effect, and I love learning that. And it gave me a big background on transport properties, so all the lingo of science that I still use to this day. But it gave me, okay, never underestimate your work, never underestimate yourself. So if you're doing something and you're being guided and someone is saying, okay, no, that's interesting, you should believe it. You should go through it. You believe in yourself. And that's why I kind of have this project, even though it was as an undergrad, like it has a special place, let's say, because it taught me a lot, not so much on the scientific part, even though, yes, but on everything else. So
that is really cool. And kudos to your supervisor as well, who is being like,
yes,
nope, you're going to write it. I'm here. If you fall, I'm here to catch you. You will learn. And it's good to build that muscle as well of, it's sad to say, but rejection in science is very, very, like, papers get rejected, your conference abstracts get rejected, your research grants get rejected. So sadly, that is the system that we work in. So it also teaches you a lot. Sometimes the rejection is for a good reason, of course, and that's when you get in conversation with the reviewers. I mean, not conversation, but in dialogue with the reviewers, that sometimes makes your paper even better.
Exactly.
That happens as well. But yeah, this is really cool. I can understand why you picked this project, because I'm pretty sure it is close to your heart.
It is. And every time I get to the citation, I'm still like, how? Okay, good, thank you.
It's good. It's good. It's good. Do not question the working system. Shush. Just accept it and go with it. That is really cool. So, Sofia, in the last almost an hour that we have been speaking, before recording and also during the recording, it is very evident for me that you love the research aspect of being a scientist, right? You love going in the lab and getting your hands dirty. Metaphorically, we are all wearing gloves and everything.
Gloves dirty.
Sorry?
Getting the gloves dirty.
Getting the gloves dirty, exactly. But what else do you like about being a scientist? Because doing research is one integral part of being a scientist, but there are a lot of other things that we often don't really talk about. So what else do you like about being a scientist?
So one of the very obvious for someone in the field, but not so obvious if you're not a scientist, is the internationality and team aspect of it. So as a scientist, you cannot work alone. Or better, you can, but you'll take 10 times the time to do something and maybe you cannot even achieve it. You need to work with other PhD students, other postdocs, your supervisor, with those postdocs and PhD students in other groups, in other countries. You need to ship samples, you need to go yourself. And this international aspect of it always captivated me so much that when I finished my PhD, I was happy to go anywhere in the world. Ended up one country next to my original one, but fun. How life goes. Still international. Learning Basque is a fun experience. But and also the teamwork aspect of it. And, you know, I don't like working alone. So this in science, that's a good field. But also the traveling and going to, because you have as a scientist, people don't think that. We think we are closed up in the lab, always running experiments and measuring. And we do that. But most of the work of a scientist is to, this sounds bad, but sell ourselves. We need to show our results. We need to show it by publishing. We need to show it by going to conferences. We need to show it by visiting another group and measuring there and sharing knowledge. And a lot of this sharing knowledge involves traveling, involves going to a conference in another continent and so on. And I really like that because I also really like traveling. So it overlaps really well. Another aspect of it, I call it, well, that's a lot to do with research, but it's the main basis, is the adrenaline. I call it an adrenaline for the mind, because when you finally figure out that result that you've been trying to figure it out, and when you finally you do a measurement and it's like, oh, this is the last piece of the puzzle that was missing. I can finally understand this. Because a lot of the times research is like you have the layout of the puzzle, you know what it should look like or what it can look like, and then you start gathering the pieces and there's a lot missing or they don't fit and you need to rotate them, you need to find how it fits, and when you finally find it, it's like poof, it's a rush. It's like in a roller coaster, the feeling, I'm not a big fan, but what people say, like when they go randomly down, it's like, oh, that rush is fantastic. So I also really like that, and it's like an addiction in a sense, like you figure out something, you finish a project and you want to start the other one, or you do both at the same time because you want to have this rush of understanding the world around you, and that's amazing.
Yeah, absolutely. Like, recently, I've been thinking about this adrenaline rush or this fascination of that moment when it clicks, when it all comes together. And that is I remember that every scientist remembers that when that happened for their master thesis or PhD thesis or any of the projects, postdoc, anything whatsoever. And I remember during my master's when I was growing the graphene, back then we were still growing graphene with chemical vapor deposition. And this was in 2013, 14, 10 years ago. Wow. It was a long time ago. And I remember, of course, we were in the clean room. I was in the clean room. I think I was alone there. And I opened the furnace and I could see the graphene on the copper because the rest of the copper oxidizes. So there is the contrast. So if your graphene flakes are big enough, you can see them with your naked eyes. And for a second, I thought, okay, is my sample dirty? And then I realized, no, this is actually graphene. And it was so cool. I really had to get out of the clean room suit and go out into by the lake that we had, and it just to calm down a bit, because it was like, finally.
It's that joke and that we want to run around screaming Eureka. We want to.
It is true. It is true. And the best part is when you're surrounded by scientists, they all get it. They all understand it. They're just like, this is amazing. And also, when we are doing the science communication, be it at the conference, what you call the selling of the results, also the room understands it, because these are the people in the field and they have faced similar questions. So they also, it just carries forward, definitely. And also the other 2 points that you mentioned, the international nature of science, I think That is so true. I have never been in more international, more diverse groups than I was while I was doing research. It's just that's just a fact, at least from my experience. And some of the most traveling people that I know are scientists. They
Yes.
are the ones who are always traveling, be it for conferences, be it for project meetings, be it for visiting other labs, other people, other institutes, and stuff. So, yeah, traveling and being a scientist, that goes hand in hand. This
Yes.
is very, very, like, at least from master onwards.
Yeah.
Probably not so much during the bachelor time, but masters, as soon as you start putting results out, I think that's totally
Yeah,
oh, I
definitely.
miss all of that. That is so cool. I'm so happy for you.
Yeah.
Yay.
Thank you. Yeah, sometimes you need other people to tell you, oh, your job is cool, so that you actually realize, yeah,
Yeah, it
it's
is
true.
very cool.
Yeah, yeah.
It is very cool. So we talked about the good sides of your job. Of course, there are downsides as well.
Yes.
So if you had 3 wishes to improve your research experience, what would you ask for? And I'm not promising anything here. Disclaimer.
Otherwise, I will
Uh,
come after you.
Sworn to the oath.
So I don't know. One of the first, like you said, science is very diverse, but still not enough.
Not enough, no.
Still not enough. And I feel like it's getting better, but there is still a stereotypical image that people have of what a scientist is. That's not true. Like, I'm probably not except being a nerd, that's stereotypical and true. I'm probably not the stereotypical image a lot of people have of a scientist. And that is not ideal, because I've noticed the more diverse a team is, the greatest things are achieved, because they come with new ideas from their background. They come, for example, me working with thermoelectrics all the way to Spintronics. I have the background knowledge of thermoelectrics, and maybe it's not expected for other in that field, and things like that. And I think we should have more diverse people at the table, and also more empathy, because not everyone will behave the same as a scientist. Like, some people are more introverted, some people are more extroverted. Some people like to ask questions after a talk. Others like to go after, find the speaker and ask all the questions, ask them all the questions. So diverse profiles exist, and we need to kind of accept them and have empathy for each other, not just, okay, this is how it should do, and this is how you should be. And that's not a great thing in science. Another thing I would say is not to look so much in the numbers. We have a lot of published, especially as a postdoc, publish or perish, that famous sentence. And it's getting better. My group here is an example, and it's getting better. We're starting to look past just the numbers. Sure, the numbers, number of citations, papers, age index, it's important, but it doesn't define someone as a scientist. They can be great in the lab and be really bad at writing, but that doesn't mean they're bad scientists. They can accomplish great things. And looking into these other, let's say, parameters of a person, of a scientist, and take them into consideration, I think we should start doing that and be like the standard, not just looking at the numbers, because it creates this pressure. And instead of focusing on doing good science, I focus, or my colleagues focus on, okay, I need to publish, I need to find what is the thing and publish, and rush for the science. You don't even enjoy it. And that's one of the things that will definitely change.
Yeah, absolutely. Yes, science is diverse, but it could be a lot better. It could definitely be a lot better. I totally agree with you on that. And this publish in Paris, I think this is now changing slightly. It is going in the right direction. It's very slow. The progress is very slow, but it is going in the right direction. So those are your 2 wishes. You still have a third one, Sophia.
I can't complain now, because and I can say that's in general for Spain, but especially here in the Basque Country, there's a lot of science is regarded as an important thing. I think science is regarded as an important thing everywhere, but then the money doesn't show that. And here I have funding, I have a great institute, I have technicians support and so on. But I've worked like in my PhD, and I wanted to do that. I had that idea. Let's do this. Oh, we can't. why? Because you don't have access to that machine, or you cannot do that, and we don't have that target, and it costs a lot. And that kind of barrier, it will exist always, but if in an ideal world, if I could have a genie granting me 3 wishes, I will remove that barrier and make science a bit more accessible in that sense. So not so much dependent, not on money, because it will depend on money, but more access to realize what are the ideas that people have, let's say, if that makes sense.
Absolutely. That makes complete sense. Not just in terms of money, but also in terms of like facilities and having access to those instruments or those materials or those data analysis softwares. It could be everything that goes with it. So that you can spend more time on doing the research and just focus on that. So yeah, all 3 very valid wishes. I hope they all come true sooner rather than later, fingers crossed. And before I let you go, Sofia, this has been a fun conversation, but before I let you go, I have one last question, and that is about part of featuring on Under the Microscope is also you get the keys to the Real Scientist Nano Twitter account for an entire week. So what can the followers, the more than 3,200 followers, expect? I know.
Not nervous at all.
No, it's good. These are all the audience who are dedicated and they want to hear about the materials and nanoscience. So what can they expect in the week that you're taking over the account?
So I will try to take you literally also into the clean room. I need to talk with the technician, but I will try to show you what is my experimental work. So what I do on a day-to-day basis. So I will take you, for example, to the clean room to show how I fabricate my materials, my devices. I will take you to how I prepare them to measure, and I will show you how we measure. I will also try to give a background on what I'm actually doing in terms of science, like we started this conversation. So explain what am I doing, what actually is the reason, what are the reasons for me to do this research, what could be the applications, and so on. Explain a little bit. And I also want to show you the other parts of being a scientist that I'm involved. So the sitting at the desk, the having to write papers, reviewers, revisions, and all this extra stuff I also do. So I'm, for example, involved in the Gender Equality Committee here in my work. I'm involved in the European Magnetism Association. I was involved in the International Association of Physics Students, all name dropping. And this is all important and actually helps, even though it makes me way too busy sometimes, it helps a lot to first distract myself because it becomes like an hobby, but also understand that my work can have great impacts and it spreads. Like if you're feeling great about your work and others also start feeling great about your work. And if you're in a team where everyone is motivated about science, or in my case, it was physics, you also get motivated yourself. So I also want to highlight this part that a lot of times gets forgotten and it's quite important. So that's kind of what you can expect from me.
Okay, that's good for a teaser for everyone to follow along and log into and check the Real Scientist Nano feed when you're taking over the account. So thank you very much, Sofia. This has been so cool and cannot wait to have you on Real Scientist Nano, of course, and following all the tweets. Thank you very much. This has been super, super wonderful.
Thank you. Thank you so much for having me. And yes, go check out all the tweets I'll be tweeting.